We're doing some real curve sketching now. So in your book you have a little recipe and you have a little spot, but I like to break it down a little bit more, and I like to have a little more space to work. So I believe in your book you should have a page where you can actually do a curve sketch like this. It might have 2 on the page, but it'll give you some room to work. So the first function we have is this polynomial, and the reason I know it's a polynomial is because there's no denominator, right? So I have to start with my curve sketching recipe, and I just go through each and everything, and that tells me a little bit more about the function. Every time I learn a little bit more about the function, I am able to sketch a little bit more of it. So first, what's the domain? So there's nothing in here that would do something illegal, right? So the domain is all real numbers. No asymptotes, no holes. So none, none, none. Okay, so we're already almost done, right? Y-intercept. Remember, the y-intercept is where x equals 0. This is where x equals 0. I shouldn't write it like that because then you'll think that it is there. This is where x equals 0. So let's set x equal to 0 and see what we get. We get y equals 0 times -1 times 2 squared. 0 times anything is 0. So that's at y equals, when x equals 0, y also equals 0. So we write this as a coordinate point, 0, 0, so that we know that that's one of the points that we're going to graph. Now our x-intercepts, we're going to do the same thing, except now this is where y is equal to 0, okay? So we say, where is this function equal to 0? And we have x times x minus 1, x plus 2 squared. Now what would make this function 0? Well, if x was equal to 0, it would be equal to 0. If x was equal to 1, it would be equal to 0. And if x was equal to -2, it would be equal to 0. So our 3 x-intercepts are going to be 0, 0, 1, 0, and -2, 0. So it's going to hit the x-axis at all 3 of those points, because any one of those points, if I put them into the function, would give me 0. Now let's look at end behavior. Is there a horizontal asymptote of any kind? Remember, end behavior is just a horizontal asymptote. This is a polynomial, so there isn't a horizontal asymptote because, again, there's nothing in the denominator. So we think the limit as x approaches infinity of this function. So what's going on in this function? When x gets really, really big, I have a big number times a big number times a big number squared. So it's just a really big number, right? So as x approaches infinity, I'm approaching infinity. I'm just getting to be a really huge number. What happens when I put a huge negative number in here, though? So I get a negative number times a negative number times a positive number. So what's going on with that? Well, a negative times a positive would be a positive number. So when x is going to negative infinity, I'm also going to positive infinity, right? So we can come up here and we can sketch this. Now, if you remember our end behavior talk from last year, you would have known that this either goes both up or both down because the degree of this function is 4, right? X times x times x squared is x to the 4th. The degree is 4, so it has to have an even end behavior. Either it goes all the way up or it goes all the way down. So let's sketch it. All right, it has no asymptotes, no holes. All we're going to do is we're going to sketch these intercepts. So first we're going to sketch that y-intercept. Then we're going to sketch the x-intercepts. That one is the same as the y-intercept. And then we have this one and this one. And then, oh, the question we have here is, are these even or odd? If you remember back to last year, even means they bounce. Odd means they go through. Okay, and we look at the power of the factor to tell us whether it's even or odd. So this is an odd one because the power of the factor is odd. This one's an odd one, and this is an even one. So we have line, line, bounce. Okay, so that means that at -2, it should bounce. So we know we start at the top, right? Because we're going, when x gets really big, y is getting really big. So we go there. We go through, we come down, we go back through, we come down, we bounce, and come back up. And there we go. We've just sketched that curve. It's not perfect because in calculus we're going to learn how to find how high up it goes and how low it goes. But this is a basic sketch of this polynomial. Our next function has a little bit more going on. See all of that stuff? Okay, so first things first, we're going to find the domain. Before we reduce anything, we always have to find the domain. Okay, so what would do something illegal in here? If we divide by 0, that's illegal. So we can't have those numbers in our domain. So our domain is going to be all reals except what would make our denominator 0. So x can't equal 0, x can't equal 1, and x can't equal 3. Any of those would give a denominator of 0. Now we're going to reduce this function so that we can see which ones of those are asymptotes and which are wholes. So what do these have in common? Well, there's an x on top and an x on bottom, so we're left with just, here's our reduced function. Remember the RED stands for reduced. I'm going to have an x on bottom still. Okay, and then I have one of those on top and one of those on bottom. So I'm going to still have one on top. And then those don't reduce because it's x plus 3 and x minus 3, and those are not the same factor. Okay, so here we go. There's our function right there. And now we can look, so which ones were wholes and which ones are asymptotes? Remember, just because one of these x's canceled out doesn't mean that it was a whole. Okay, one of them canceled out, but one of them stayed. So in the reduced function, anything that is still in the reduced function is still a vertical asymptote. So 0 is going to be a vertical asymptote. We're going to have one at x equals 0. We're also going to have an asymptote at x equals 3. Where do we have a whole? Anything that's no longer left on the bottom of the reduced function, that would be 1. So our x equals 1 is going to be our whole, and we'll look at that here in a minute. Now, are each of these functions, or these vertical asymptotes, even or odd? It's tricky. Because right here, if we looked at our original function, we would have a different answer than if we looked at our reduced function. Well, guess what? We always look at the reduced function, okay? So anything that crosses out, we ignore it when we're trying to find whether our vertical asymptotes are even or odd. So the power of this x is odd, so this is an odd vertical asymptote. The power of the other factor, though, x minus 3, is even, so this is an even vertical asymptote. So I can go ahead and start graphing these, right? I've got a vertical asymptote at 0, and I've got a vertical asymptote at 3. Okay, and I know what they're going to look like. I know that at 3, they're either both going to go up or both going to go down, and I know at 0 they're going to be opposites of each other. So let's figure out what that looks like. So we're going to look at the limit as x approaches each of these vertical asymptotes. So first, let's try approaching the vertical asymptote 0 from the left and see what happens. Okay, when I'm approaching 0 from the left, I have to pull my function up here. I'm going to get let's see, we're going to put numbers a little bit smaller than 0 in here. So if I put a number a little bit smaller than 0, I get a negative number here. If I put a number a little smaller than 0, I get positive. So negative times a positive. So I can keep track of this. I have negative times a positive on top. And then on the bottom, if I have a number just slightly smaller than 0, that's a negative. And then the other one is a negative number, but it's squared, so it's going to be a positive. So what do I get? I get a negative over a negative, which is a positive. So the limit as x approaches 0 from the left is going to be a positive number. So it's going to be positive infinity. What happens when it approaches 0 from the right? We're going to have a number slightly bigger than 0, but that's still going to give us a negative, and that's going to be positive. But this one down here, this number is going to now be a positive number, right? Because it's going to be like 0.1 or something like that. And then this one's going to be positive because it's always positive. So we have positive, positive. Now, what do we get? Well, we get negative infinity. So as x approaches 0 from the right, it's going to be negative infinity. Okay, so I know that we're going to go as x approaches from the left, we're going to positive infinity, so we're going to do like that and like that. That gives me an idea. All right, let's look at the other asymptote. So the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. We're always just going to look at both of these limits and see what's going on. And this is an even asymptote, so it should be the same on both sides. So let's pick a number that's just slightly bigger than 3. Or actually, let's go smaller than 3 first. So you have 3 minus 1. Like 3.1 minus 1, that's going to be positive. 3.1 plus 3 cubed is going to be positive. 3.1 is going to be positive. Oh, that's a number bigger than 1. See, I said it, and then I went back on myself. And then 3.1 minus 3 squared is always going to be positive. So I have positive, 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 positive. So this is going to go to positive infinity. Since it's even, it should do the same thing. We could check it by doing a number that's slightly smaller than 3. And if we have like 2.99, then 2.99, that's still going to be positive, that's still going to be positive, that's still going to be positive, and that's still going to be positive. So we have positive infinity for both of these, so they're both going to positive infinity. So we know that this one's going to go something like that. Okay, so that's a start. Now we go to the next one, the whole. All right, so we know we had a whole at positive 1. So we have a whole at positive 1 when x equals 1. Now what's the other coordinate of that whole? Well, we plug 1 back into the reduced function, which is this one right here. So we have 1 minus 1 is 0. And then none of the rest of it matters because 0 divided by anything is 0. So we know we have a whole at 1, comma, 0. So we graph that, 1, comma, 0 is a whole right here. And is it even or odd? Well, the function, the factor that created this whole was an odd power. So this is going to be an odd whole, meaning it's going to go straight through. It's not going to bounce off and go back. So, which makes sense, right? Because that's the way the function has to go. All right, we're looking for y-intercepts now, but guess what? This has an asymptote at 0, so we automatically know there's no y-intercepts. You could try, but when you try to plug 0 into this function, you're going to get 0 on the bottom, and that's not okay. So there are no y-intercepts. And then we look for x-intercepts. So we set this function equal to 0. And we remember that we're only looking in the reduced function for x-intercepts. Because if something exists in the first function but doesn't exist in the second function, then it's a whole. So it wouldn't be an x-intercept, it would just be a whole on the x-axis, which we already see. I'm not drawing very well because I'm trying to talk at the same time. All right, so we just look at the reduced function for our x-intercepts. And let's see, when this is equal to 0, we have to set the top equal to 0. We don't care about the bottom. So 1 is going to be an x-intercept. And negative 3 is also going to be an x-intercept. So we go up here, we graph 1, which is a whole. Even though it was reduced out, it's still got that extra one there, so it's still whole. We still don't graph it. It doesn't exist, because that would still create a problem in our function. And then at negative 3. 1, 2, 3. So this one's actually not an x-intercept because it's a whole. If there's a whole where we think there's supposed to be an x-intercept, it's just not an x-intercept. It's just a whole. Okay. Finally, we look at end behavior. We ask, is there an asymptote? Is there a horizontal asymptote? And we look, and it doesn't really matter which one we look at because the degree is going to be the same. So this has a degree of 4 up here, and this has a degree of 3 down here if we multiplied them all out. So there's no horizontal asymptote. So the limit as x approaches infinity and as x approaches negative infinity would be either negative infinity or positive infinity. We just have to decide. If I put a huge, 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 huge number in here, what am I going to get? I'm going to get positive, 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 positive. So as x approaches infinity, y is also approaching infinity. So it's going to go like that. As x approaches negative infinity, it's going to end up negative. So it's going to go like that. So then we just connect our dots. And we know that this one doesn't come down because there's no more x-intercept.